welcome to Classical Mechanics 2. In this video, we'll learn about Emmy Noether and her eponymous theorem. Emmy Noether was one of the most influential mathematicians in all of the 20th century, but few people have heard her name. In this video, I'm going to tell you a little bit about her life and her work, then we'll spend some time discussing her famous theorem that relates continuous symmetries to conserved quantities in physical systems. Emmy Noether was born in 1882 in Erlangen, Germany. She wanted to study mathematics, but at the time, women were only allowed to audit classes. So in the winter of 1903-1904, while she was at the University of Göttingen, she audited classes taught by mathematicians, including David Hilbert, Felix Klein, and Hermann Minkowski. When she returned to Erlangen in 1904, she was finally able to study mathematics there. She earned her PhD in 1907 with a dissertation on algebraic invariance. In 1915, David Hilbert and Felix Klein invited her back to Göttingen to help them work on some of the mathematics behind the theory of general relativity. She eventually decided to remain there, but the rest of the faculty were not okay with women teaching at the university. So she was only allowed to lecture in classes when they had Hilbert's name officially on the transcript. In 1918, she came up with her famous theory in theoretical physics. A copy is shown here. Beyond theoretical physics, she was interested in a lot of different types of algebra and was an absolutely extraordinary mathematician. In 1920, she published concerning moduli and non-commutative fields, particularly in differential and difference terms, in the journal Mathematische Zeitschrift. This was a phenomenal paper and finally made the mathematics community take note of her achievements. Throughout the rest of her career, she studied non-commutative algebras. She also edited Mathematische Annalen, or the Annals of Mathematics, which is an incredibly important journal. And she was part of the most exciting mathematical research going on at the time in Göttingen. Then in 1933, the Nazis came to power in Germany, and Noether and many other Jewish professors at Göttingen were dismissed. As a pacifist, Emmy Noether did not feel that she could be safe in Germany, so she accepted a post as a visiting professor of math at Bryn Mawr College in Pennsylvania. She lectured and continued her research there and at the Institute for Advanced Study in Princeton. Emmy Noether died in 1935 following complications from an operation to remove an ovarian cyst. Sadly, the extent of her influence in mathematics cannot ever be accurately known, for much of her work appeared in publications of students and colleagues, most of whom had male names. Sometimes they would mention that she offered insight or was there to help complete some idea, but none truly gave her the credit that she deserved. Now we'll take some time to discuss Noether's theorem. We'll look formally at the statement and how to put it into math. Then we'll look at the consequences of this for mechanics. Noether's theorem states, every continuous differentiable symmetry of the action has a corresponding conserved quantity. Our action, S, is given by the integral from time t1 to time t2 of the Lagrangian as a function of the generalized coordinates q, their derivatives q dot, and time integrated over dt. Consider a change in coordinates. We've done this before from Euclidean coordinates to generalized coordinates, but here we'll call our new coordinates s. They are functions of some continuous parameter zeta for each of the original qi's. We say that the action has a continuous symmetry if the Lagrangian in the new coordinates s, s dot, and t is equal to the Lagrangian in the original coordinates q, q dot, and t for all values of the parameter zeta. Noether's theorem states that c is equal to the sum on I of dl by dsi dot times dsi by d zeta is the corresponding conserved quantity. And we're going to derive this next. What does it mean for a quantity to be conserved? Let's start with a system with a continuous symmetry. The Lagrangian in terms of the initial coordinates q, q dot, and t must be equal to the Lagrangian in terms of the new coordinates s of zeta, s dot of zeta, and t. Here's a path, let's call it gamma 1. Gamma 1 is the path that minimizes the action for the coordinates q. This path here, gamma 2, minimizes the action for the coordinates s. Let's look at what happens if we expand s for small values of zeta. Then the difference between the starting points of the two paths is equal to p1 times delta zeta. and the difference between the endpoints of the two paths is equal to p2 times delta zeta. The action of the path gamma 2 is equal to the action of the path gamma 1 plus ds by d zeta times delta zeta. If S of zeta really is a continuous symmetry of the system, then by definition the action of the second path is equal to the action of the first path. And this term, ds by d zeta, must be equal to 0. Or equivalently, the total derivative of the Lagrangian with respect to zeta must be equal to 0. We can expand the total derivative of the Lagrangian as dl by ds times ds by d zeta plus dl by ds dot times ds dot by d zeta. Then we'll use the definition of the Euler-Lagrange equation to rewrite dl by ds. That gives us d by dt dl by ds dot times ds by d zeta plus dl by ds dot times ds dot by d zeta. And what we can do is undo the chain rule. So the first term has d by dt acting on dl by ds dot, and the second term has d by dt acting on ds by d zeta. Next, we want to undo the chain rule, and we get d by dt acting on dl by ds dot times ds by d zeta is equal to 0. This means that this quantity, dl by ds dot times ds by d zeta, is a constant of the motion. And we say that because its rate of change is equal to 0. Being a constant of the motion means that we get this first integral for free. When we integrate this term, we get a constant. And this constant of motion is our conserved quantity, dl by ds dot times ds by d zeta. Let's see how these symmetries show up in some of the physics that we've seen before. Let's start by looking at a continuous translational symmetry. For example, a 2D system with gravity, where our initial coordinates are given by x and y. Then my Lagrangian in these coordinates is 1/2 m x dot squared plus y dot squared minus mgy. In the x direction, I can pick the origin of my coordinate system anywhere. So I can write it generically as x tilde is equal to x plus a. Then in these coordinates, my new Lagrangian L tilde is equal to 1/2 m x tilde dot squared plus y tilde dot squared minus mgy tilde. And for this to be a continuous symmetry of the system, this must also equal the original Lagrangian L. You'll note that x tilde dot is equal to x dot because a is a constant. So the new and old Lagrangians are going to be the same regardless of the value of a. On the other hand, y goes to y plus b is not a symmetry of the Lagrangian. This is because the gravitational potential energy depends on y. So the potential energy at y is not the same as the potential energy at y tilde equals y plus b. Then the conserved quantity here is dl by dx dot times dx tilde by dA plus dl by dy dot times dy tilde by dA. The second term here is 0 because it doesn't depend on a. The first term, I get mx dot times dx tilde by dA, which is equal to 1. That gives me mx dot. So my conserved quantity is momentum in the x direction. That's a really powerful statement because it relates the symmetry of my space to the actual physical quantities in the system. More generally, if my potential energy u of x is equal to u of x plus zeta for all zeta, then x goes to x plus zeta is a continuous symmetry of the Lagrangian. It follows then that du by d zeta is equal to 0 since the potential energy doesn't depend on the value of zeta. This tells us that the system is now force-free in the x direction. This is the fundamental mathematical basis of Newton's first law. If there are no forces in a given direction, then its momentum must remain constant. This is another beautiful result that just comes out of the formalism of Lagrangian mechanics. Let's repeat the analysis we just did, but for rotational symmetries now. Let's try measuring a rotational system in terms of some new coordinates. Theta tilde is equal to theta plus alpha. Our Lagrangian then is the kinetic energy, or 1/2 I theta dot tilde squared, minus the potential energy, u of theta tilde. And this is going to be the same as the Lagrangian in our old coordinates, 1/2 I theta dot squared minus u of theta. Then our conserved quantity here is dl by d theta dot times d theta tilde by d alpha, and this is equal to I theta dot, which is the definition of angular momentum. So having a system that is rotationally symmetric, that is a system where the origin of the angular component doesn't matter, that means we're guaranteed to have conservation of angular momentum. In my opinion, Noether's theorem is the most profound idea in the entire undergraduate physics curriculum. This is such a powerful statement because it applies to physics regardless of the type of system or the length scale you're studying. We've approached it from the vein of classical mechanics, but it applies equally well in quantum mechanics or general relativity or quantum field theory. This is something that exceeds the boundaries that we've set up between physical disciplines. In the next video, we'll use Noether's theorem to derive conservation of energy and use that to derive the Hamiltonian. Thanks for watching, and I'll see you next time.